we are starting Gary Taylor's chapter 5, which turns out to be in the AP curriculum. It is really the end of unit 5, sort of like 5.8 on. And it really has more to do with connecting the relationship between derivatives and the function itself. And this is not, like this particular section in Gary Taylor, curve sketching, this is not something you really have to do in the AP curriculum, but we're going to do a little tiny bit of it. And mostly I'm just going to do the work with you today because I just think the problems are overly complicated. So we're going to do some homework questions together, really, just for practice. And so, curve sketching recipe, pay attention to domain. So pretty important you remember that domain comes from the denominator. Denominator domain. This is going to give us things like, if we can reduce the function, can we factor and cancel anything? Because if we can factor and cancel something, that's going to give us holes in our function. So factor and cancel gives us the holes. And then whatever is left over in the denominator gives us vertical asymptotes. So vertical asymptotes come from the denominator of a reduced function. We can find x and y intercepts by plugging in zeros. An x-intercept is when we plug in a 0 for the y, and a y-intercept is when we plug in a 0 for the x and solve for y. So pretty easy to plug in zeros to get those intercepts. Now, we can also use the derivatives to also help us sketch the curves, and that's the entire what we're trying to really learn is the relationship between the derivatives and the shape of the curve, okay? So if we take the first derivative, then we know where our function is increasing and decreasing. We can also find those maximum and minimum, relative maximum and minimum points. And if we look at the second derivative, then we can talk about concavity. So whether something is concave up or concave down. And so all of those things really come together to kind of help sketch the curve. So what we're going to do is I'm just going to actually skip all the problems. The assignment, and I have it on the calendar in Google, we're going to just do number 1, 3, 4, 5, 9, and 13 through 21. So we're going to do a bunch together today, and then whatever we don't finish, you guys just do for homework. 13 through 21 is mostly easy, easy stuff, matching. Okay, and so the goal here is, without using a calculator, we want to find the local extrema, the maximums and minimums, inflection points, and sketch a graph. It's not necessary to find x-intercepts, and these first couple have no domain restrictions, but knowing in behavior will be helpful. So that's what we're going to do. We're just going to work together here. This is 5.1, numbers 1, 3, 4, 5, 9, and 13 through 21. All right, so number 1 is y equals x cubed minus 3x squared plus 5. Now, of course, I can absolutely plug this into my calculator and sketch the curve. It's not hard to do because we have calculators to do it. But what we're trying to do is figure out how things are really related with calculus, and it's kind of a cool thing. So, you're here. Oh, blessed. Welcome. All right, excellent. I can stop recording. Can I stop recording? I'll record. I'll keep recording because you're taking a test. Okay. Do you want me to take your backpack?
No, I thought I was there recording.
Oh, God, again? Yeah.
That's not
Whew. All right. Did you sign in the office?
Yeah,
Okay.
yeah.
Oh, killy dokily. Okay. We know the overall shape of this curve. Talking about M behavior, the leading term here is x to the third. And if you talk about EB is for M behavior. Where does it, like, where are the arrows? For instance, if it was x squared, what shape is that? Parabola. Where are the arrows? Both going up. So you have an arrow in quadrant 2 and an arrow in quadrant 1. And there's this, stuff in between. So if it's positive x cubed, where are the arrows? Yeah, so quadrant 3, and then stuff happens in the middle, and then quadrant 1. So an odd function always has arrows in the third and first quadrant. If it's negative, then it'd be going the other way, 2 and 4, okay. Okay, so the M behavior is we have basically it starts low and ends up high. That's how I think about it. Anyway, all right, we want to do a couple of things, and I think for this problem, I'm going to start by taking a derivative. What is the derivative of our function? Minus 6x, great. And from here, we can use our derivative to figure out where our curve is increasing and where it's decreasing. So we're going to do that by setting it equal to 0. And I can try to factor it. What can we factor out of our little equation here? 3x. 3x comes out. What's left behind? X minus 2. So we get an x equal to 0 and an x equal to positive 2. And these are, this is y prime. So at 0 and 2, these are the possible relative max and relative min. And we just need to see what's going on here. So to the left of 0, I'm going to test some numbers here. Like negative 10. If I have a negative 10 in place of x, I'm going to have negative times negative, which is going to give me a positive. Between 0 and 2, I can test like a 1. And if I plug in a 1 for x, I get positive times negative. So that would be a negative result. And to the right of 2, like positive 10, I'd have a positive value and a positive value. Positive times positive is positive result. And so by looking at our first derivative number line here, we're going from increasing to decreasing, uphill to downhill. So that makes this a maximum, a relative maximum at 0. And then we're going from downhill to uphill, so decreasing to increasing. So this would be a relative minimum at 2. Now what we can actually do to help us graph this is this gave us a lot of points here. If I find the y value when I plug in a 0, I get 5. That's a point on the curve. That is a point on my function, and it is the maximum of the curve. So we just found a nice point to graph on our function pretty easily. If I plug in a 2 cubed minus 2 cubed is 8 minus 12 is negative 4 plus 5 is 1. Yes. Okay. So we have a minimum at 2, 1. We can do one more thing pretty easily, is take our second derivative. What is the second derivative? 6x minus 6, very good. And again, we can set that equal to 0. And this is going to determine concavity for us. I can factor out a 6, or you just solve it. It doesn't matter. So we get x equals 1. And again, little number line here. Oh, that's supposed to be a 1. To the left of 1, we might have 0. So that's going to be negative. And then to the right of 1, like plugging in a 10, we'd have positive times positive is positive result there. And so you can see right here, we do have a point of inflection because we're changing from concave down to concave up. So at 1 is a point of inflection. So we're changing concavity, concave down to concave up. So I'm going to write that in. Concave down. Over here, we're concave up. If I plug in a 1, this is to my original function. 1 minus 3 is negative 2 plus 5 is 3. So that is a point of inflection. So I have a bunch of points that I can graph on my curve here. I'm going to make a little sketch now. Got a lot of information. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I have a few things here. I know that I have a relative max at 0, 5. 1, 2, 3, 4, 5. So I'm maxing out here. So thinking that's the maximum of a curve. And then at 2, 1, I'm at a relative minimum. 2, 1, right there. 2, 1. So this is a minimum, relative minimum. And then at 1, 3, right here, that is a point of inflection where we're changing from concave down to concave up. So everything to the left of 1 has this concave down shape, which makes sense because I have a relative maximum there. So everything to the left is concave down, and everything to the right of 1 has to be concave up. There we go. Concave down, concave up. That's our curve. Now, if you really want to see, it's kind of fun to compare. So you can actually, I just like doing this because I think I love graphing functions. I think it's probably the coolest thing about look at that. Pretty good. Crossed at 1, not, or close to 1, not negative 2, but that's okay. This wasn't factorable. Like if we were able to factor the original function, we could have found the x-intercepts. But it's not factorable, so we have no idea. All right, so there you go. Concave down, concave up, very cool. What's the concave up part? All right, let's try another. Number 3. Y equals x to the 4th minus 4x cubed plus 16. Once again, I would try to factor this if I could, but because it's a 4th degree and it's not like x to the 4th and then x squared, I can't possibly factor it. So I'm going to go ahead and just think about what's the end behavior. How should the arrows go if it's a positive x to the 4th function? Arms up, yeah? So it should do something, step in the middle and then end up high as well. So quadrants 2 and 4, crazy stuff in the middle. But that's our expectation. So it's always good to know where you're headed. All right, so y prime, what is the first derivative? 4x cubed minus 12x squared. Great. I'm going to go ahead and set that equal to 0. What could we take out of there? A 4 and? Not just an x? X squared. Which leaves behind what? X minus 3, good. All right, I'm going to set each thing equal to 0. We get x equals 0, and here we get x equals 3 for our critical numbers. So 0, we have a potential max or minimum. All right, this is y prime. All right, numbers to the left of 0. So if I plug in some large negative values, and then I square them, I get positive things. And here we get negative things. So positive times negative is negative stuff. Between 0 and 3, I could plug in an easy number like 1. So if I plug in a 1, I get a positive result here and a negative result for this bubble. Negative again. To the right of 3, something big like 10. Here we get positive values, and here we also get positive values. Positive times positive is positive. So because they're going from decreasing to increasing, this is decreasing to increasing. At 3, we would have a relative minimum. What's happening here? It's going to decreasing, and then it hits out at a 0 slope, and then it goes to decreasing again. Kind of an interesting thing there. But it's going downhill, and then it sort of levels out to have a slope of 0, and then it's going downhill again. So kind of interesting right there. Let's see. So I don't know what's happening, but it's kind of a critical thing here. I'm going to go ahead and figure out what the value is at 0 because it's easy. So I can just plug in zeros, and I get 16. And y at 3 is a little bit harder. Definitely harder, but I did the math, and it's negative 11 when you plug in a 3 to that. And those aren't really things that you need to know, but they are kind of helpful. All right, let's go ahead and find a second derivative. What would our second derivative be? 12x squared minus 12. Oh, 24. X. Yeah? Yeah? Okay. 12x squared minus 24x is equal to 0. All right, and then we can take out what? A 12 and x. I take out a 12x, what's left behind? So setting those equal to 0, we get x equals 0 and x equals 2. So these are potential points of inflection. They do have values of 0. Let's see. So to the left of 0, plugging in a negative number, we get negative times negative, which would be a positive result. Between 0 and 2, I'm going to plug in a 1, let's say. So I'd have a positive here and a negative value there. We get a negative result. Good. And to the right of 2, something like positive 10, I get positive and positive. All right, so we do have a couple points of inflection here. We're changing from, again, concave up to concave down, and then back to concave up. And so we definitely have some points of inflection here. Points of inflection. So at 0, again, we get 16 in our original function. And plugging in a 2, I think we also get 0. Yeah, okay. All right, so we've got a lot of information going on here. I'm not going to graph all the way up to 16, but 1, 2, 3, 4, 1, 2, 3. I'm just going to pretend. I think I'm going to count these by 2. Okay. I guess I'm almost there. 16. Okay. Okay, but these are going to be 1. Let's see. So a couple things here. At 0, 16, that turns out to be a point of inflection, in which case we're changing from concave up to the left of that, and then concave down to the right of that. And so that's kind of a nice thing. So you can see the concave up part and then concave down. There's really a lot of information just with concavity in terms of the shape. And then we have a minimum at 3, negative 11? 3, negative 11. Okay. Negative 2, negative 4, 6, negative 8, negative 10. Okay, at 3, negative 11 right here, that is a minimum. So I know it's a local minimum way down there. And we also have a point of inflection at 2, 0 right here. So everything between 0 and 2, this is all concave down. And then at 2, it switches to all concave up. All right, there we go. There's our curve. So concave up, then go concave down, switches to concave up. And we know that it's supposed to end with our arms, 2 arms pointing upward there. So kind of interesting. Let's see. X to the 4th minus 4x cubed plus 16. I'm going to change the window. That's fine. My y max, I got to go beyond my minimum. I'm going to go negative 15, and my maximum, I'm going to go 20. So you can see our curve fairly well. Pretty cool, eh? I think it's pretty neat. It's kind of, I think it's really cool. But I'm a math teacher. What do I know about being cool? Okay. Okay. Now, I really like 4 and 5. I think they're great questions, but also this is definitely a useful thing to know, so I really wanted to spend some time with these as well. So f of x equals x squared minus 2x minus 8. We want to find the intercepts on this one and give the relative extrema. So find the max and min as well to graph these functions. So to find our intercepts, I know that I can plug in a 0 for x, and I get negative 8 very easily. That is the y-intercept. To find the x-intercept, I can take my function and factor and solve. So f of x equals x squared minus 2x minus 8, and I'm just going to double bubble. All right, how does x squared minus 2x minus 8 factor? Yeah, x times x is x squared, negative 4 and positive 2 gives us that center, negative 2. That's good. So we get x equals 4 and x equals negative 2. And so those are our x-intercepts. At 4, 0 for the function, and negative 2, 0 for the function. All right, then I can go ahead and find our relative extrema, so relative max and min. That's a first derivative thing. So what is our first derivative of our function? 2x minus 2. Setting that equal to 0, we get x equals 1. And I'm going to go ahead and do a quick number line at 1. To the left of 1, like 0, we would get a negative result. And to the right of 1, like 10, we would get a positive result. And so we're going from decreasing to increasing, which means we have a minimum, a relative minimum at 1. And so I can go ahead and figure out what that minimum value is by plugging 1 in. 1 squared minus 2 is negative 1. Minus 8 is negative 9. I'm good, right? Yeah? Okay. All right. So, sketching our curve. I had x-intercepts at 4, 0, and -2, 0, where we cross the x-axis. I have a relative minimum at 1, -9, which I'm going to pretend is right here. Which also, you know, we could have done this the algebra 2 way. If you can find your x-intercepts, where is the minimum or maximum? In the middle. So between -2 and 4 is 1, and then you just plug it in. Anyway, you could have done it. This is the arms up, and it's just a parabola. But there's a reason we're doing this. So there's your graph, very easy to do. And you can see here, we're going from decreasing downhill slopes to increasing to the right of 1. So, all right, all calculus, it's all calculus. Okay, so why did we do that? We did that for number 5. Number 5 is g of x, and it is the absolute value of what we just did. Okay, and this is the beauty of Gary Taylor's work that I love so much, is that there's a reason we did this easy problem, so that now you know how to do this. Okay, what does absolute value do to something? It just turns it positive, doesn't it? Okay. And because of that, anything, so this is the function, the original curve is this parabola. We've just graphed it. And if you put an absolute value around that whole thing, all it's going to do is take anything that's negative and flip it positive. Okay? And so all it does is take that whole section down here that's in negative land, and it just flips it around. So we still have our zeros at -2 and 4, and our curve to the left is the same, and our curve out to the right is the same. But in between, we're flipping the script here and going 1 +9. And now this is a very complicated curve, but it's not, is it? So all we're doing is taking everything in down negative land and flipping it above the x-axis. It just takes all those y's and turns them positive. And so this is the kind of thing now where this is a really interesting curve now. Before we were all concave up here, but because the absolute value really switches things up, we're concave up, concave down for this whole section, and then concave up. So it really changes kind of a lot of things there. But this kind of thing is important to know, because they do a lot of this on the AP test, or they're like, what's going on here? And if you have an understanding of, hey, I know what the original curve looks like, well, it's just going to flip it up, then you can really go a long way thinking through things. All right, does that make sense to you? All right, very cool. All right, let's see. Another one I want to talk about was number 9. Without a calculator, find the domain x-intercepts and relative extrema points in graph f of x. There are no points of inflection. So we have, again, another interesting function. And these kinds of functions come up quite often. So again, I like to talk about these. So to start us off here, we need to talk about domain. Domain normally comes from the denominator, but this is a radical function, a square root function. So for domain, what do we know? Greater than or equal to 0. It's allowed to equal 0, yeah. So anytime you have a square root function, and it's particularly any even square root. Odds doesn't matter. All right, so when you, the way that I remember these things is that I know that the cube root graph, the cube root of x, it looks like this. It goes forever to the left and forever to the right. It has the domain of all real numbers. But when I think about the square root graph, the square root of x, It's the square root swoop. Looks just like the shape of it. And it's equal to 0 and to the right. And so it's everything greater than or equal to 0. So I really just remember the shape. It's the same for any even function. So a 4th root and a 6th root and an 8th root, all are kind of similar. So for any even root, we know that that thing has to be greater than or equal to 0. Well, this is often a pretty complicated thing. I can get rid of my root by squaring both sides. We're left with 9 minus x squared is greater than or equal to 0. Do you know how to solve this? You cannot just isolate x. That only works on linear things. All right. So this is asking a very different question. It's saying, hey, where is this curve greater than or equal to 0? And so, again, I like to approach this sort of thing graphically. We can double bubble this. 3 times 3 is 9. What times what is negative x squared? Positive x times negative x. And so what's happening here is we know this is a parabola. Is it an up parabola or a down parabola? Down parabola, yeah. It's got negative x squared, so it's a down parabola. And it has intercepts at negative 3 and positive 3. So what's happening here is we have an easy curve here at negative 3 and positive 3. And we know that it's going downward. And so this is asking the question, hey, where is this parabola greater than or equal to 0? Well, to the left of negative 3, it's negative. Between negative 3 and 3, it's positive. And to the right of 3, it's negative again. So where is the curve greater than or equal to 0? Yeah, for x values between negative 3 and positive 3. We could write it negative 3 to 3 in interval notation if we wanted to. That is the domain right there. And again, I like talking about that because this is something that, I don't know, it doesn't come up a ton in pre-cal. I spend a lot of time on it in pre-cal because we have to know it in calc, okay? But I think probably most teachers spend like a day. But we'll do it with all kinds of curves, just to solve non-linear inequalities. Interesting thing. So the domain of this function, the only place we see it is between negative 3 and 3. Let's see, what else did we need to find? We need to look at the derivative. So f prime, what time are we at here? 8:51. Oh, we're almost done. Oh, darn. All right, we want to look at the derivative. This is 9 minus x squared to the 1/2 power. How do we take the derivative of that? Nine minus x squared to the negative 1/2 power. Don't forget, almost, negative 2x. Chain rule, got to take the derivative of the inside anytime you got something more complicated than just x. Don't forget to multiply by the chain rule. All right, I'm going to do a little bit of cleanup here. The times by 2 and divide by 2 cancel one another out. And so this is, I have a negative x in the numerator. And in the denominator, I have a square root of 9 minus x squared. So just to rewrite that, and I think is a more understandable way. We've already figured out that the denominator can only be between negative 3 and positive 3. But we can set this thing equal to 0. If we were to do that, we would cross multiply. The denominator goes away because 0 times the denominator is just 0. So we get x is equal to 0. So that is a critical number. So f prime at 0. If I plug in negative values, like negative 1, If I plug in -1, I'd get positive on top and positive on the bottom. And if I plug in, oh, and I'm between -3 and +3, so you can't plug in anything, just between -3 and 3. So plugging in +1, we would get a negative on top and a positive on the bottom. So we're going from increasing to decreasing, and that makes at 0 a maximum. F of 0 is the square root of 9, which is just 3. 1, 2, 3. Did you know the shape of this graph? It is a semicircle. So the domain is equal to 0 at 3 and -3. Our function is equal to 0 at 3 and -3. The maximum here is at 0, 3. It is just a semicircle. Interesting, right? All right, well, that's that graph. Which you can see on your calculator. This is nothing that you can't see, graph, like these aren't difficult, but I did them because I just was pretty sure you guys didn't really know what they looked like. You can see the difference on your calculator. The calculator just sort of stops graphing. However, if I change the window, let's see what happens if I go from -3.1 to +3.1 and -0.1 to 3.1 on the Y. Again, you can see it. It seems like it stops graphing, but it does actually go all the way to the axis. And that's the difference between knowing and using your calculator. And that's only because the calculator has this like parameters set up. If it feels too much of a pixel, it sort of stops graphing because it has to pass the vertical line test. And anyway, so the pixels are not, it's not a retina display. Anyway, there we go. I think on the rest of these, 13 through 21, I don't know, give them a try. I was hoping to get through them, but maybe we'll finish this tomorrow instead of talking more. Okay. Right here, there you go. 13 through 21. Give them a try. We'll talk about them more tomorrow because I think they're really valuable to do together. Now, you can definitely try 17 through 21. So if you do anything, do 17 through 21. And we'll talk about 13, 14, and 15 tomorrow. How about? Okay? All right.